Our next topic is 5.3, Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus has two parts, and we're actually going to go over part 2 first. It says if f is continuous on the closed interval from a to b, then the integral from a to b of f of x, little f of x, is equal to big F of b minus big F of a, where big F is any antiderivative of little f. That is, a function such that big F prime equals f. So this is the 4.9 relationship we talked about with antiderivatives in the same notation. So big F is the antiderivative of little f, and when you take the derivative of big F, you get back to f. That's what it means to be an antiderivative. So it turns out that that section is related to what we've learned as the definite integral. So if we think about this a little bit, this is actually a really profound result. We don't have to use 5.2 anymore to evaluate most integrals. So we can just find the antiderivative, big F, evaluate it at b, then evaluate it at a, and then take f of b minus f of a. So this gives us a shortcut to doing the problem with the limit of the Riemann sum for an integral. So this is great. There's a proof in the book, and you can look at that on your own time if you want to, but I'm actually just going to do an application example that illustrates why this works. So suppose you set a car on cruise control at 60 miles per hour and drive for 3 hours. How far have you driven? So the way that you can figure this out is with our d equals rt, because it's a constant rate. And so if you're going 60 miles per hour for 3 hours, you just take 60 times 3, and the distance you will have traveled is 180 miles. So it's a little weird, but notice if you plotted time versus velocity, or the rate of 60 miles per hour, the distance is the area of that rectangle. So this is what I've shown graphically, that if we plot that the velocity function is 60, it's just a line, flat line, and our axis, y-axis, is representing the velocity, or the speed. And then our independent variable t is like our x-axis. And so taking r times t, that would correspond to taking the height of the rectangle times the width, which is defined by the time, and you get 180 units squared, which is, in this interpretation, the distance. So kind of a weird thing to do, but that's just motivation for Part B. Part B says suppose you travel at the speed as a function of time at, changes to a speed as a function of time shown in the graph. Estimate the distance traveled in 3 hours. So looking at this graph, we have a more realistic situation that somebody is taking off in their car and they're driving some pretty slow, and then they're probably going on to the freeway or the highway and they're able to drive more around like 60 miles per hour. But that's going to fluctuate a little bit with hills and other situations. So if we wanted to estimate the distance traveled, we could use the same concept as part A and use the equation d equals rt on intervals. Those would correspond to finding the area. I use midpoint in this situation. So for the first half hour, you would take your, that's down here, your half hour, I'll just highlight it quick here, in blue, you would take your half hour times the midpoint for your velocity or rate on that interval as 20. And so continuing in that way, for each subinterval, then what you would have is all these little kind of like RTs multiplied together for subintervals to get estimates of the distance for each subinterval. So this should look familiar. we get an answer of 140 miles. This is exactly what we did in 5.1. And this is exactly what a definite integral is. So we're going to get to that connection with what we're doing a little bit. It says if we know the rate over time, velocity in this case, we can interpret distance as area under the rate curve. In this case, we have x is equal to t. So look at this in symbols. The integral from 0 to 3 of the velocity function is equal to the total distance traveled in those 3 hours. So this could be found by taking your position function, if you knew it, evaluated at t equals 3, minus the position function evaluated at t equals 0, if you knew the position function. But from what we learned about antiderivatives in 4.9, we do know what the position function is if we know the velocity function, because the position function is the antiderivative of the velocity function. So if we take this result, or this observation, and write it in general, then the integral from a to b of little f of x is equal to big F of b minus big F of a, where big F is the antiderivative. So this is just showing that, yes, this makes sense, even though at first glance I think this is probably not obvious at all. And this is what the fundamental theorem of calculus is saying, part 2.